We are asked here to differentiate from first principles the function f of x is 2 over x squared. Now, if we have a function that we want to differentiate, one way to consider it, let's say we have a function, say mentioned here, and let's evaluate the function at a point x, and we'll evaluate it at another point given by x plus h. Now let's work out the gradient of the line joining those 2 points. So when we join the 2 points, here we can see we have, well, in this case, a negative gradient, but the gradient of this line would be given by, here we have f of x plus h, here we have f of x, so the gradient would be given by the function evaluated at x plus h minus the function at x divided by x plus h minus x. But of course, you can see this is not the gradient at the point here. As we move this point closer to x, that is, if we reduce h, you can see gradually the gradient of this line connecting the 2 points will become closer and closer to the gradient at x. And that is where our formula for differentiation from first principles comes from. It says that the derivative f dashed of x is the limit as h becomes very small and in fact goes to 0 of the function evaluated at x plus h minus the function evaluated at x, all divided by h. Well, let's see what happens now for our function here, f of x being 2 over x squared. The function is 2 over the square of the input. So, with the particular case, f of x is 2 over x squared, what do we get? The limit, as h tends to 0, f of x plus h, 2 over the square of the input, 2 over x plus h, all squared, minus f of x, 2 over x squared, all divided by h. Now what we can't do at this point is just set h equal to 0. If h was equal to 0, the two terms on the numerator would be equal, the numerator would be 0. If h was 0, the denominator would also be 0. We need to do a little bit more work on this. So we have the limit as h tends to 0, well, whole thing divided by h. But now let's express the two terms here with a common denominator. And that common denominator will be x plus h all squared times x squared. So 2 over x plus h all squared will be 2x squared over this common denominator, and 2 over x squared will be 2 times x plus h all squared over this common denominator. You can see 2x squared over x squared times x plus h all squared. The x squares will cancel. We'll get the 2 over the square of x plus h. and then minus 2, well, those squares will cancel, we get 2 over x squared. And of course, we can write this 2x squared minus 2 x plus h all squared over x plus h all squared x squared h. And again, we cannot simply set h equal to 0. We'd get 0 on the denominator and indeed 0 on the numerator. Let's instead expand out our numerator. So denominator x plus h all squared x squared h. Numerator, well, 2x squared, and we subtract off 2 times x squared plus 2xh plus h squared. Well, what happens here? 2x squared minus 2x squared. Those cancel. Well, let's write them down. 2x squared minus 2x squared. We also have minus 2 times 2xh. That's minus 4xh minus 2h squared. And on the denominator, we still write x plus h squared x squared times h. And yes, we get a bit of cancelling now. The top line simply becomes, this and this disappear, minus 4xh minus 2h squared, and on the bottom line, x plus h all squared x squared h. And one thing that we notice now is that there's a common factor of h on top and the bottom. So when we cancel this common factor of h, because h is only tending to 0, we're not simply setting h equal to 0. So on the top, minus 4x, cancelling this h, minus 2h, because we're cancelling the second h, and we're also cancelling the h here. X plus h all squared times x squared. And now finally, we can set our h equal to 0, take the limit, this term will disappear, so we get minus 4x minus 0, x plus h all squared will be x squared times x squared, so we get minus 4x over x to the 4, or 4 over x cubed. So we can now say that from first principles, if f of x is equal to 2 over x squared, then f dashed of x is minus 4 over x cubed. We've carried out the differentiation from first principles.